Across 140 million miles of radiation-soaked vacuum, a spacecraft carries human beings toward a rust-colored world that may never let them leave. This is not science fiction. This is not a cautionary tale whispered in the corridors of mission control. This is the unspoken reality of Mars exploration, hidden beneath press releases and animated mission timelines that show smiling astronauts planting flags and returning home as heroes. But physics doesn't care about narratives. And the mathematics of interplanetary travel tells a far more disturbing story, one that space agencies frame carefully, that engineers understand deeply, and that the public has never fully confronted. Tonight, we journey into the shadow side of humanity's greatest dream, the parts of Mars missions that don't make it into recruitment videos or congressional testimony. The moment a spacecraft leaves Earth's gravitational embrace, bound for Mars, something profound happens. Not just physically, but psychologically. Astronauts have described it in hushed tones, the way Earth transforms in the window. First, it's a world, continents and oceans rotating beneath swirling white clouds. Then, within hours, it becomes a sphere, beautiful but distant, hanging in the darkness like a decoration on velvet. And then, after days of continuous travel, it becomes what Carl Sagan called it, a pale blue dot. A pixel of light suspended in the cosmic dark, barely distinguishable from the stars around it. But this time, something is different. This time, that pale blue dot may be the last clear view of home these travelers will ever have. Because the physics of returning from Mars, the actual engineering reality beneath the inspirational rhetoric, is so monumentally difficult that every serious mission architecture encounters the same brutal truth. Bringing humans back may be functionally impossible with current technology. This is not a failure of imagination, it is a constraint of reality. The rocket equation, that merciless mathematical law governing all spaceflight, demands that every kilogram of fuel you want to use for the return journey must itself be lifted from Earth, along with fuel to lift that fuel, and fuel to lift that fuel's fuel, in an exponentially crushing spiral of mass and energy. To launch enough propellant from Earth to refuel a Mars return vehicle would require a spacecraft so massive, so expensive, and so complex that no space agency has yet designed one that survives contact with budget committees or physical reality. So instead, mission planners speak carefully. They talk about in-situ resource utilization, the elegant phrase for making fuel on Mars itself. They discuss sustainable architecture and long-duration surface operations. They show timelines stretching across decades, implying that return is simply a matter of patience and technology maturation. What they don't say, what lives in the margins of technical papers and the silences of engineering reviews, is that we are planning to send people on a journey from which return is, at best, theoretical. Why the silence? Perhaps because humanity has always needed heroes who come home. Perhaps because funding dies the moment you say one-way mission out loud. Or perhaps because the truth is too heavy to carry, that the price of becoming an interplanetary species might be measured not just in dollars and years, but in lives spent beneath alien skies, watching Earth rise and set as an unreachable memory. Before we drift deeper into this disturbing physics, I'd like to ask something of you. In the comments below, tell me where you're watching from and what time it is in your part of the world. Because this video is about distance, isolation, and the profound weight of being far from home. And right now, We're all scattered across this single fragile planet, separated by time zones and geography, yet connected by curiosity. Let's see how far across Earth this question reaches before we talk about reaching across worlds. Now let us begin with the mathematics of entrapment, with the rocket equation that makes prisoners of us all, and with the 140 million mile problem that wants you dead. Before we can understand why returning from Mars is nearly impossible, we must first confront a mathematical truth that has governed every journey into space since the dawn of the rocket age. It is an equation so simple in its form, yet so devastating in its implications, that it shapes every aspect of space exploration. This is the rocket equation, formulated by Konstantin Tsiolkovsky in 1897, and it is both our guide and our prison. The equation itself appears innocent. Delta V equals exhaust velocity multiplied by the natural logarithm of initial mass divided by final mass. Written on paper, it occupies a single line. But within this elegant mathematical statement lies a tyranny that has broken the dreams of every mission planner who has dared to imagine human journeys beyond Earth's orbit. The rocket equation does not simply describe how spacecraft move through the void. It dictates the fundamental limits of what is possible, and more importantly, what is not. At its core, the equation reveals a cruel reality. To go faster, you need more fuel. But that additional fuel has mass, and to carry that mass, you need even more fuel, which itself has mass, which requires still more fuel. The relationship is not linear, it is exponential. This is the tyranny. Every additional kilogram of payload demands not just 1 kilogram of fuel, but multiple kilograms, compounding upon themselves in a cascade of increasing mass that grows without mercy. Consider the journey to Mars. To escape Earth's gravity well and embark on the 140 million mile voyage requires a change in velocity, a delta V, of approximately 3.8 kilometers per second. The spacecraft must accelerate to this tremendous speed, fighting against Earth's gravitational embrace with every meter gained. Using conventional chemical rockets with exhaust velocities around 4.5 kilometers per second, this translates to a mass ratio of roughly 2.3 to 1. For every kilogram you wish to send to Mars, you must begin with 2.3 kilograms on the launch pad. More than half of your spacecraft's initial mass is simply fuel that will be consumed in the first stage of departure. But the numbers become truly disturbing when we consider the return journey. Escaping Mars's gravity, though less demanding than Earth's due to the planet's smaller mass, still requires a delta V of approximately 4.1 kilometers per second to begin the voyage home. The mass ratio for this maneuver is even worse, roughly 2.5 to 1. Every kilogram returning from Mars must be accompanied by 1.5 kilograms of propellant just to leave the Martian surface. Here is where the exponential nature of the rocket equation reveals its full brutality. The fuel needed for the return journey is not separate from the outbound journey. It is part of the payload, which means you must carry it with you from Earth, which means you need additional fuel to lift that return fuel out of Earth's gravity well, which itself requires more fuel. The masses multiply backward through the mission profile, like dominoes falling in reverse, each stage demanding more from the one before it. NASA's own calculations reveal the stark mathematics. A typical Mars mission architecture shows that approximately 40% of the total fuel budget is consumed simply reaching Mars. The remaining 60% exists to facilitate everything that follows: landing on Mars, living on Mars, launching from Mars, and returning to Earth. But this distribution masks a deeper problem. That 60% of fuel must be carried during the initial 40% expenditure, dramatically increasing the mass that must be lifted from Earth's surface. The rocket equation compounds at every step. To understand the scale of this challenge, consider the Apollo missions to the Moon. The Saturn V rocket that carried astronauts to lunar orbit weighed 2.97 million kilograms, fully fueled. Of this enormous mass, only 45,000 kilograms reached lunar orbit, a mere 1.5% of the initial mass. The vast majority, over 98%, was propellant and tankage, discarded in stages as the rocket fought its way out of Earth's gravitational well. Yet the Moon is practically next door compared to Mars, requiring far less delta V, and offering a return journey measured in days rather than months. Mars is fundamentally different. The journey takes not days but months. The distances are not thousands of kilometers but hundreds of millions. The communications delay alone transforms every decision into an act of faith, every problem into a potential catastrophe unfolding in slow motion. And the rocket equation cares nothing for human aspirations. It simply calculates mass ratios with mathematical indifference. Consider a thought experiment. Imagine a spacecraft designed to carry 4 astronauts to Mars and return them safely to Earth. The habitat module, life support systems, radiation shielding, supplies, and scientific equipment might mass 50,000 kilograms, a conservative estimate for an 18-month journey. Using conventional chemical propulsion, the propellant required for the return journey alone would mass approximately 75,000 kilograms. But this propellant is now part of the payload that must be carried from Earth, which means the outbound journey must lift not just 50,000 kilograms, but 125,000 kilograms, which requires an additional 162,500 kilograms of propellant for Earth departure. The spacecraft that begins the journey would mass nearly 300,000 kilograms, of which only 50,000 kilograms serves the actual mission. The rest is fuel to carry fuel to carry fuel, and this assumes no contingencies, no backup systems, no margin for error. In reality, mission planners would demand redundancy, additional supplies, emergency reserves. The mass spirals further upward, each safety measure adding kilograms that demand more propellant, that demand more tankage, that demand larger structures, that demand still more propellant. This is why every kilogram becomes your enemy, not because mass itself is inherently problematic, but because the rocket equation transforms every addition into a multiplication. A 10-kilogram scientific instrument does not simply add 10 kilograms to the mission mass. It adds 23 kilograms at Earth departure, and perhaps 15 kilograms of propellant that must be manufactured or carried from Earth for the return journey. The total mission cost of that single instrument might be 40 or 50 kilograms multiplied backward through every stage of the journey. Mission planners agonize over these calculations. Every decision becomes a negotiation with physics. Do we include extra food supplies or additional radiation shielding? Do we bring more scientific instruments or more spare parts? Each choice is a trade against the rocket equation's exponential demands. Engineers speak of mass budgets, the way accountants speak of financial budgets. Because in space exploration, mass is the currency that purchases capability, and the exchange rate is brutal. The Apollo program succeeded despite these challenges because the Moon offered advantages that Mars does not. The lunar journey required only days, not months. The landing sites were chosen for accessibility, not scientific value. The lunar module was stripped to its absolute essence, little more than an engine, a fuel tank, and an aluminum foil wrapper around 2 standing astronauts. There were no seats, no toilet, no comfort. Every unnecessary kilogram had been sacrificed to the rocket equation's demands. Mars offers no such compromises. The journey duration alone demands massive life support systems. Radiation shielding cannot be eliminated without condemning the crew to lethal exposure. Food, water, oxygen, power systems all must function reliably for years, not days. And unlike Apollo, where mission control could offer real-time guidance, Mars astronauts face communications delays of up to 22 minutes each way. They must carry not just supplies, but autonomy, which means redundancy, which means mass. Some have proposed nuclear thermal propulsion, which offers higher exhaust velocities and thus better mass ratios. Others suggest electric propulsion, efficient but agonizingly slow. Still others dream of nuclear pulse propulsion or antimatter drives, technologies that remain firmly in the realm of science fiction. Yet even with advanced propulsion, the rocket equation's tyranny merely lessens. It does not disappear. The disturbing truth is that the rocket equation makes return from Mars exponentially harder than the outbound journey. Not twice as hard, not 3 times as hard. Exponentially harder, in the mathematical sense of the word. Each additional requirement for the return mission multiplies backward through the entire mission architecture, demanding more fuel, more tankage, larger structures, until the spacecraft that departs Earth bears little resemblance to anything humanity has ever built. This is why every kilogram is your enemy. And this is why, when we speak honestly about Mars missions, we must confront the possibility that return may not be physically impossible, but may be practically impossible, given current technology and economic reality. The rocket equation does not negotiate, it does not compromise, it simply calculates, with cold mathematical precision, the price that must be paid for every journey into the cosmic dark. The distance to Mars changes every day, not metaphorically, but literally. As we speak, the gap between our world and the red planet shifts, widening and narrowing in a celestial dance governed by laws written into the fabric of space-time itself. This is not a journey measured in miles alone, but in windows of opportunity that open and close with indifferent precision. Miss your chance, and the universe makes you wait. Not hours, not weeks, 26 months. When we imagine traveling to Mars, we often picture a simple line drawn through space, a straight path from one world to another. But the cosmos does not grant us straight lines. Instead, it offers curves, ellipses, gravitational wells, and trajectories that must be calculated with such precision that an error of seconds can translate into millions of miles. The path to Mars is not a road, it is a negotiation with orbital mechanics, and the terms are unforgiving. The most efficient route to Mars is called a Hohmann transfer orbit, named after the German engineer Walter Hohmann, who first described it in 1925. This trajectory is elegantly simple in theory. You launch from Earth when Mars is ahead of you in its orbit around the Sun. Your spacecraft follows an elliptical path that intersects Mars's orbit precisely when Mars arrives at that same point. It is cosmic choreography, a rendezvous timed not by clocks, but by the movements of worlds. The journey takes approximately 6 to 9 months, depending on the specific alignment. But here is where the mathematics of return begin to reveal their cruelty. Once you arrive at Mars, you cannot simply turn around. The orbital mechanics that brought you here have fundamentally changed. Earth is no longer where you left it. Mars and Earth are now positioned such that attempting an immediate return would require impossible amounts of fuel and energy. The Hohmann transfer that worked in one direction does not work in reverse, not without waiting for the planets to realign. This is the 26-month problem. Earth and Mars orbit the Sun at different speeds. Earth completes its orbit in 365 days. Mars takes 687 days. The geometry of their positions creates launch windows, brief periods when the energy requirements for transfer are minimized, and these windows open only once every 26 months. If you miss your departure window from Mars, you do not get to leave early. You do not get a backup flight. You wait stranded on an alien world for more than 2 years until the planets drift back into favorable alignment. Imagine the psychological weight of that waiting. You have survived the journey. You have landed safely. You have completed your mission. But the return trip is not a matter of readiness or will. It is a matter of celestial mechanics grinding forward at their own implacable pace. During those 26 months, every system must continue functioning. Every seal must hold. Every filter must work. Every psychological support structure must endure. The clock does not care about your supplies running low or your mental state deteriorating. The clock is planetary, and planets move according to laws far older than human anxiety. Even when the launch window arrives, the energy requirements for return are not symmetrical. This asymmetry is one of the most disturbing aspects of Mars travel. On Earth, we launch from a world with strong gravity, requiring enormous energy to escape. But Earth also has a thick atmosphere, allowing for aero-braking on return, which saves fuel. Mars presents the opposite challenge. Its gravity is only 38% of Earth's, making launches easier. But that same reduced gravity means Mars holds you in a shallower but still significant gravitational well. Delta V, the change in velocity required for orbital maneuvers, becomes the currency of survival. To escape Mars' orbit and begin the journey home requires approximately 5.7 kilometers per second of delta V. This is less than escaping Earth, but it is still substantial. More importantly, once you leave Mars, you must have enough velocity to return to Earth, slow down upon arrival, and survive atmospheric entry. Every meter per second of velocity requires fuel. Every kilogram of fuel adds mass. Every kilogram of mass requires more fuel to move. The equation spirals, demanding resources that may simply not exist on Mars when you need them most. Mars's orbit is not circular. It is elliptical, more so than Earth's. At its closest approach to the Sun, perihelion, Mars is about 128 million miles from our star. At its farthest point, aphelion, it stretches to 154 million miles away. This eccentricity creates additional timing complications. The ideal launch window depends not only on the relative positions of Mars and Earth, but also on where Mars sits in its own orbital path. Launch at the wrong point in Mars's ellipse, and you add months to your journey, or exponentially increase your fuel requirements. The geometry becomes even more complex when considering the inclination of Mars's orbit relative to Earth's. The two planets do not orbit in precisely the same plane. Mars's orbital plane is tilted about 1.85 degrees relative to Earth's. While this seems minor in the vastness of space, this inclination requires additional corrections, additional fuel, additional precision. Every variable compounds, every margin narrows. Perhaps the most counterintuitive trap is that Mars's 38% gravity, while dramatically less than Earth's, is still too much. It is not gentle enough to escape easily, yet not strong enough to provide the same engineering advantages we have at home. On Earth, we use the atmosphere for aerobraking, deploying parachutes and heat shields to slow incoming spacecraft without burning fuel. Mars has an atmosphere, but it is thin, less than 1% the density of Earth's. Aerobraking on Mars is possible for arrival because you are traveling at high velocity, and even a thin atmosphere can slow you down when you hit it hard enough. But for departure, that same thin atmosphere offers almost no assistance. You cannot glide into orbit on Mars. You cannot use airflow to gain altitude. You must burn fuel relentlessly, fighting against gravity with nothing but chemical thrust. The limitations of Martian aerobraking for return trajectories are severe. While spacecraft arriving at Mars can use atmospheric friction to bleed off speed and achieve orbit, the reverse is not true. Launching from Mars's surface requires a powered ascent through that wispy atmosphere, which provides negligible lift, but just enough drag to be a nuisance. Once in orbit, departing for Earth requires another substantial burn. The fuel costs accumulate in ways that Earth-based intuitions fail to predict. Some engineers have proposed using Mars's atmosphere creatively, dipping a departing spacecraft into the upper atmosphere repeatedly to gain velocity through aerodynamic effects, a reverse aerobraking maneuver. But the mathematics are unforgiving. Mars's thin air cannot provide the necessary impulse without dozens or hundreds of passes, each one risking structural failure, heat damage, or orbital decay. What works for slowing down does not work for speeding up. The gravitational well of Mars is a trap precisely because it sits in an uncomfortable middle ground, too deep to escape trivially, too shallow to offer the atmospheric or gravitational assists we rely on at Earth. It is a gravity well designed by indifferent physics to maximize the difficulty of return. Once you descend into Mars's embrace, climbing back out requires resources, planning, and luck in measures that test the boundaries of current technology. Every trajectory back to Earth must account for arrival conditions. You cannot simply aim at Earth and hope for the best. You must intercept Earth's orbit at the precise moment Earth is there, traveling at speeds that allow for capture rather than a catastrophic flyby. Miss by days, and you sail past Earth into deep space. Arrive too fast, and atmospheric entry becomes a fireball that no heat shield can survive. The margin for error is measured in meters per second and minutes of arc across millions of miles. Orbital mechanics does not negotiate. It does not offer second chances or sympathetic alternatives. The laws that govern planetary motion were set in motion billions of years ago, and they will continue unchanged long after humanity is gone. When we speak of returning from Mars, we are not discussing a simple reversal of our journey. We are describing a new mission, one that must be planned with the same meticulous care as the outbound trip, executed during a narrow window that opens briefly and then closes for more than 2 years. The 140 million mile problem is not the distance itself. It is the realization that distance and space is not static. It breathes. It changes. It creates conditions that shift between possible and impossible with the slow, inexorable movement of worlds. To journey to Mars is to enter a gravitational and temporal maze where the exit may not appear for years, and when it does, it demands resources and precision we may not possess. Here, in the mathematics of orbits and the calculus of delta V, we confront a disturbing truth. The universe does not care if we survive. It offers pathways, but it guarantees nothing. The return journey from Mars is not impossible, but it is profoundly, disturbingly difficult. And difficulty, when measured across millions of miles and months of waiting, begins to resemble impossibility. The question is not whether we can calculate the trajectory home. The question is whether we can carry enough fuel, endure enough time, and maintain enough precision to execute that calculation when the moment arrives. And whether, after 26 months of waiting on an alien world, we will still have the capacity to try. We land on Mars. The journey is complete. The spacecraft settles onto rust-colored soil, and the crew emerges to witness a new world. But beneath the triumph of arrival lies a question that has haunted mission planners from the beginning. How do we go home? The answer, according to nearly every Mars mission architecture ever proposed, is deceptively simple. We make fuel. Not on Earth, not in orbit, but here on Mars itself, using the planet's own resources. This concept, known as in-situ resource utilization, or ISRU, sounds like elegant engineering, a solution so obvious it feels inevitable. Take carbon dioxide from the Martian atmosphere, combine it with hydrogen, apply energy and chemistry, and produce methane and oxygen, the propellants needed to launch a spacecraft back toward Earth. On paper, it is beautiful. In reality, it is one of the most audacious gambles ever proposed in the history of space exploration. The promise begins with Mars itself. The planet's atmosphere is 95% carbon dioxide. It is thin, barely 1% the pressure of Earth's atmosphere, but it is everywhere, freely available to anyone who can capture it. The chemistry is well understood. The Sabatier reaction, developed over a century ago, converts carbon dioxide and hydrogen into methane and water. Add electrolysis to split the water into hydrogen and oxygen, and you have both components of rocket fuel. Methane burns with oxygen. Heat expands. Thrust is generated. A rocket climbs towards space. SpaceX has built its entire Mars colonization strategy around this idea. The Starship vehicle is designed to refuel on Mars, producing approximately 900 tons of propellant needed for the return journey. NASA's Moon to Mars architecture includes ISRU as a foundational technology. Without it, the mass of fuel required for a round trip becomes so enormous that the mission collapses under its own weight, strangled by the rocket equation before it even begins. But here is where the dream meets the Martian surface, and the surface, it turns out, is unforgiving. The Sabatier reaction itself is not theoretical. It works. We have demonstrated it in laboratories on Earth, in controlled environments with reliable power, abundant feedstocks, and technicians standing by to adjust parameters when things drift out of specification. The reaction requires carbon dioxide, hydrogen, heat, pressure, and a catalyst, typically nickel or ruthenium. Feed these ingredients into a reactor at the correct temperature, around 400 degrees Celsius, and methane emerges on the other side. The question is not whether the reaction works. The question is whether we can make it work on Mars continuously for years, with no supply shipments, no replacement parts, and no second chances. Consider first the energy requirements. Producing 900 tons of propellant demands enormous power. Estimates vary, but most analyses suggest you need somewhere between several hundred kilowatts to multiple megawatts of continuous power, sustained not for days or weeks, but for months or even years. Where does this energy come from? Solar panels are the obvious answer. Mars receives sunlight, though only 40% as intense as Earth. You could deploy vast arrays of photovoltaic panels, covering hectares of Martian terrain, angling them toward the pale sun, hoping dust storms do not bury them, hoping the electronics survive temperature swings from warm afternoons to nights where carbon dioxide freezes out of the air. But solar power on Mars is intermittent, seasonal, and unreliable. Dust is not just an inconvenience. It is a constant adversary, coating panels, reducing efficiency, demanding cleaning systems that themselves require power and maintenance. Nuclear power offers an alternative. A small fission reactor could provide steady, uninterrupted energy regardless of dust, night, or winter. But as of now, no flight-ready nuclear reactor capable of generating megawatt-scale power exists for Mars deployment. NASA's KiloPower project has demonstrated a 10-kilowatt reactor, scaling that up by a factor of 100, ensuring it can operate safely on another planet without human intervention for repairs, is not merely an engineering challenge. It is pioneering an entirely new category of space technology. Then there is the hydrogen problem. And this, perhaps more than anything else, exposes the fragility of the ISRU dream. The Sabatier reaction requires hydrogen, lots of it. Mars has carbon dioxide in abundance, but hydrogen is scarce. There is some water ice at the poles, possibly buried in subsurface deposits at lower latitudes, but accessing it means drilling, heating, extracting, purifying. Every step adds complexity, energy cost, and failure points. The alternative is to bring hydrogen from Earth. But hydrogen is the lightest element in the universe, and also one of the most difficult to store. It leaks through container walls. It requires cryogenic cooling to remain liquid. Transporting tons of hydrogen across interplanetary space, keeping it cold for months, then storing it on Mars while fuel production proceeds, is an engineering nightmare wrapped inside a logistical puzzle. And if you are bringing hydrogen from Earth, you are undermining the entire premise of ISRU. The point was to avoid hauling massive quantities of material to Mars. If you must bring a significant fraction of your propellant feedstock anyway, the advantage diminishes, the mission mass increases, and the rocket equation tightens its grip once more. Let us assume, for a moment, that these problems are solved. Assume you have energy. Assume you have hydrogen. Assume the reactor is running. The Sabatier process is producing methane, and electrolysis is splitting water into hydrogen and oxygen. Now you must store it. Methane must be kept at cryogenic temperatures, around negative 160 degrees Celsius. Oxygen must be stored at negative 183 degrees Celsius. On Mars, daytime surface temperatures can rise above freezing, but nights plunge well below. Keeping propellants cold requires active refrigeration, more energy, more equipment. Letting them warm means pressure builds inside tanks. Too much pressure and the tanks rupture. Too little insulation and propellant boils away faster than you can produce it. This is not a fuel depot. This is a chemical plant operating in one of the harshest environments humans have ever attempted to reach, running autonomously with no technicians, no supply chain, and no room for error. And then there is time. Producing 900 tons of fuel does not happen quickly. Even optimistic projections suggest it will take 1 to 2 years of continuous operation. Some estimates extend to 3 years or more. This means your ISRU system must be sent to Mars before the crew arrives, landed successfully, deployed, and activated remotely. It must run flawlessly for years, while Mission Control watches from Earth, helpless to intervene if something breaks. What happens if a pump fails? What if a valve sticks? What if Martian dust, fine as talcum powder and electrostatically charged, infiltrates a seal or clogs a filter? On Earth, maintenance is routine. On Mars, a single mechanical failure could mean the entire fuel production system goes silent, and the return spacecraft sits empty, a monument to optimism stranded on an alien world. We tell ourselves these are solvable problems, and perhaps they are. Engineers are capable of extraordinary things, but we must be honest about what we are proposing. We are asking a chemical factory, built on Earth, tested in terrestrial conditions, to operate on Mars without direct human oversight, for years, producing the single most critical resource for the crew's survival, with no backup, no redundancy that does not add mass, and no possibility of resupply if something goes wrong. SpaceX's vision requires this technology to work, not eventually, not in some distant future, but soon, within the timeline of missions planned for the next decade. Yet as of now, no full-scale ISRU system has been tested on Mars. No prototype has produced even a kilogram of propellant in Martian conditions. The largest demonstration, NASA's MOXIE experiment aboard the Perseverance rover, produces oxygen at a rate measured in grams per hour, enough to sustain a small instrument, not a rocket. Scaling from grams per hour to tons per month is not iteration. It is transformation. It is the difference between a proof of concept and an operational system upon which human lives depend. The fuel nobody can make is not impossible, but it exists for now, primarily in mission proposals, in PowerPoint slides, in the confident projections of engineers who believe, rightly, that challenges exist to be overcome. Whether belief is enough, whether the technology will mature in time, whether we are willing to send humans to Mars, knowing their return depends on machinery that has never been proven beyond Earth. These are questions we have not yet answered. And until we do, the return journey remains not a plan, but a hope, not a guarantee, but a gamble on chemistry, on engineering, and on the unforgiving patience of a planet that offers nothing freely, not even the fuel to leave. As our spacecraft leaves Earth's orbit, pushing toward Mars, something changes. It is not dramatic. There are no alarms, no sudden shifts in temperature or pressure. The change is invisible, silent, and relentless. We are crossing a threshold that humanity evolved never to cross. We are leaving Earth's protective magnetosphere, the invisible shield that has sheltered all life on our planet for billions of years. Beyond this boundary, space is not empty. It is filled with radiation so pervasive, so penetrating, that every cell in your body becomes a target. The journey to Mars takes approximately 7 months. The return journey, assuming everything goes perfectly, takes another 7 months. But between these 2 voyages, you must wait on Mars for the planets to realign, a stay of roughly 18 months. In total, a round trip to Mars exposes you to deep space radiation for approximately 500 days. 500 days during which subatomic particles, traveling at nearly the speed of light, pass through your spacecraft, through your suit, through your skin, and directly into the nuclei of your cells. This is not hypothetical danger, this is physics, and physics does not negotiate. The radiation environment beyond Earth's magnetosphere comes from two primary sources, each with its own character, its own lethality. The first is galactic cosmic rays, or GCRs. These are high-energy particles, primarily protons and helium nuclei, accelerated to tremendous speeds by supernovae and other violent cosmic events occurring across the galaxy. They have been traveling through space for millions of years, and when they finally encounter your body, they do so with energy so high that conventional shielding becomes nearly useless. GCRs are the background radiation of the cosmos itself, a constant bombardment that never stops, never varies significantly, and cannot be avoided. The second source is solar particle events, or SPEs. These are sudden bursts of radiation ejected by the Sun during solar flares and coronal mass ejections. Unlike GCRs, which arrive steadily, SPEs are unpredictable and can flood a spacecraft with dangerous radiation in minutes. During a major solar event, an unshielded astronaut could receive a lethal dose in hours. On Earth, our magnetosphere deflects these particles harmlessly into space. On Mars, with its thin atmosphere and no global magnetic field, you are exposed. During the journey between worlds, you are even more vulnerable. The numbers are sobering. Current estimates suggest that a round-trip Mars mission would expose astronauts to approximately 1.1 sieverts of radiation. To put this in perspective, the annual radiation exposure limit for workers in nuclear power plants is 0.5 sieverts. An astronaut on a Mars mission would receive 20 times this amount. The consequences are not immediate. Radiation does not burn or blind you in deep space. Instead, it works quietly, breaking chemical bonds, damaging DNA, increasing the probability of cellular mutations. Each particle that strikes your body leaves behind a microscopic trail of destruction, and over 500 days, these trails accumulate. The cancer risk is perhaps the most discussed consequence. Studies estimate that this level of exposure adds approximately 5% to an astronaut's lifetime risk of developing fatal cancer. For context, if your baseline risk of dying from cancer is around 20%, a Mars mission increases it to 25%. This may sound acceptable, a calculated risk that explorers have always taken. But cancer is not the only concern. It is not even the most immediate one. What troubles researchers more is the emerging evidence of central nervous system damage. High-energy cosmic rays do not simply pass through your brain. They interact with it. Studies on mice exposed to simulated deep space radiation have shown alarming results. Cognitive decline, memory impairment, reduced problem-solving abilities, and behavioral changes. The damage is caused by the heavy ions in cosmic rays, particles like iron and silicon nuclei that create dense tracks of ionization as they penetrate neural tissue. These tracks can destroy synapses, kill neurons, and trigger inflammatory responses that persist long after the initial exposure. Imagine arriving at Mars after 7 months in deep space. Your mission requires you to make critical decisions, operate complex machinery, and respond to emergencies with precision. But your cognitive abilities have degraded. Your reaction times are slower. Your memory is unreliable. You struggle with tasks that would have been routine on Earth. This is not fatigue or psychological stress. This is physical damage to the structure of your brain, caused by particles you never saw, never felt, and could not avoid. The instinct, of course, is to shield against this radiation. If the danger comes from particles in space, why not simply add more material between the astronauts and the void? The answer lies in the unforgiving mathematics of mass. Effective radiation shielding requires enormous amounts of material. To reduce GCR exposure by even 50%, you would need to surround the crew compartment with several feet of water, polyethylene, or other hydrogen-rich materials. This adds tons of mass to the spacecraft, mass that must be accelerated, decelerated, and maneuvered. Every kilogram of shielding requires more fuel, which requires more structural support, which requires even more fuel. The tyranny of the rocket equation applies to radiation protection just as ruthlessly as it applies to everything else. Moreover, shielding can sometimes make the problem worse. When high-energy cosmic rays strike dense materials like aluminum, they can create secondary radiation through a process called spallation. The incoming particle fragments into a shower of lighter particles, some of which may be even more biologically damaging than the original ray. This means that adding conventional metal shielding can, paradoxically, increase the radiation dose inside the spacecraft. Hydrogen-rich materials perform better because they absorb energy without producing as many secondaries, but they come with their own challenges. Water freezes, plastics degrade, and both require massive volumes to be effective. Some proposals suggest using the spacecraft's water supply, food stores, and even human waste as radiation shielding, arranging them around a central storm shelter where astronauts could retreat during solar particle events. This is clever engineering, but it addresses only one of the two radiation sources. It can protect against sudden solar flares, but it does little against the constant bombardment of galactic cosmic rays. And even if you could shield effectively, you would still face another cruel reality: the return journey. After spending months on Mars, exposed to surface radiation, your body is already damaged. Your cells have accumulated mutations. Your tissues have been stressed by the continuous assault of cosmic rays striking the Martian surface. Mars offers no magnetic field to deflect particles and only a thin atmosphere, providing roughly 1% the shielding of Earth's atmosphere. Living on Mars is like living at high altitude on Earth, but with far worse radiation exposure. And then, when the launch window finally opens, you must climb back into a spacecraft and endure another 7 months in deep space. This second leg of radiation exposure is not simply additive. Your body's repair mechanisms have been working overtime for over a year and a half. DNA repair enzymes, which fix the breaks caused by radiation, can become overwhelmed or less efficient with accumulated damage. The return journey pushes your total exposure well beyond safe limits, into a range where long-term health consequences become not just probable, but nearly certain. Perhaps the most disturbing implications are not for the astronauts themselves, but for the future of Mars colonization. Radiation does not only cause cancer and cognitive decline, it damages reproductive cells. Both eggs and sperm are vulnerable to radiation-induced mutations, and these mutations can be passed to offspring. Studies on animals exposed to space radiation suggest increased rates of genetic abnormalities in subsequent generations. If humans are to establish permanent settlements on Mars, they will be doing so in an environment that continuously damages their DNA, including the DNA they would pass to their children. This raises profound questions about the biological future of a Martian population. Would children born on Mars, conceived by parents whose germ cells were irradiated throughout their lives, face higher rates of birth defects or genetic diseases? Would multiple generations of Martian colonists experience accelerated evolutionary pressure, selecting for individuals with more robust DNA repair mechanisms? Or would fertility itself decline as damaged reproductive cells fail to produce viable embryos? The radiation environment of Mars is not something we can engineer away easily. Unlike temperature or atmospheric pressure, which can be controlled inside habitats, radiation permeates everything. It passes through regolith, through walls, through water tanks. Living underground offers some protection, and thick layers of Martian soil above a habitat can reduce surface radiation significantly. But this means that Martian colonists would spend most of their lives in tunnels and caves, rarely venturing to the surface, except when necessary. The vision of humans walking freely across Martian plains, exploring red deserts beneath a butterscotch sky, becomes a fantasy. The reality is closer to confinement, to a life spent avoiding the very planet you travelled so far to reach. The radiation gauntlet is not a single event. It is not a storm to weather or an obstacle to overcome. It is the persistent, inescapable background condition of interplanetary travel. Every moment spent beyond Earth's protective embrace is a moment in which your body is being altered at the molecular level. The journey to Mars and back is not just a test of engineering or courage. It is a biological gamble, a wager that your cells can endure what evolution never prepared them for. As we look toward Mars, we must confront this reality with clear eyes. Radiation is not a problem we can solve with better rockets or smarter computers. It is written into the structure of space itself, a consequence of living in a universe filled with high-energy particles and distant exploding stars. To leave Earth is to accept damage, to return is to accept more, and for those who would stay, building lives on a world without a magnetic shield, the radiation gauntlet does not end. It becomes their permanent condition, a slow and silent rewriting of what it means to be human. We arrive on Mars, stepping onto red soil beneath a butterscotch sky. The journey is over. Humanity has reached another world. Yet as the dust settles around our boots, a different kind of journey begins. One that does not take place across millions of miles, but within the very architecture of our own bodies. Mars, with its gentle 38% of Earth's gravity, seems forgiving at first. Movement becomes effortless. Lifting equipment feels almost playful. But gravity is not merely the force that keeps us grounded. It is the silent sculptor that has shaped every bone, every muscle, every system within us across millions of years of evolution. And on Mars, that sculptor has abandoned its tools. The human body is not designed for Mars. It is designed for the exact gravitational pull of Earth, calibrated across countless generations to function under 1G. Remove that force, reduce it to just over a third, and the body does not adapt. It rebels. Slowly, quietly, irreversibly. What begins as a feeling of lightness becomes, over months, a transformation so profound that the question is no longer whether we can live on Mars, but whether we can ever return home. Within the first weeks on Mars, the process begins. Bone density loss. On Earth, our bones are constantly rebuilding themselves, responding to the mechanical stress of gravity, of walking, of simply standing upright. But on Mars, that stress is diminished. The body, efficient as it is, begins to economize. Why maintain dense, heavy bones when they are no longer needed? The skeleton starts to dissolve itself from within. Studies aboard the International Space Station, where astronauts experience microgravity far more extreme than Mars, show bone loss at a rate of 1 to 2% per month. On Mars, with some gravity still present, the rate may be lower, but it does not stop. 18 months on the surface, the minimum stay required by orbital mechanics before a return window opens, could mean a loss of 15 to 20% of bone density. The hips, the spine, the legs all begin to thin, becoming fragile, porous, brittle. What was once a sturdy frame becomes something closer to glass. And it is not just the bones. Muscle atrophy follows with relentless precision. Even with rigorous exercise, 2, 3, even 4 hours daily, astronauts cannot prevent their muscles from wasting away in reduced gravity. The body simply does not need the strength it once did. Walking on Mars requires less effort. Lifting objects becomes easier, and so the muscles, starved of their evolutionary purpose, begin to fade. The legs weaken first, then the core, then the back. Muscles do not just shrink in size, they change in composition, losing fast twitch fibers, the ones needed for explosive movement, for catching yourself when you fall, for standing up quickly. After 18 months, the legs that carried you across Earth may struggle to support your own weight when you return. The cardiovascular system, too, begins its quiet collapse. On Earth, the heart works constantly against gravity, pumping blood upward from the legs, maintaining pressure, keeping oxygen flowing to the brain. On Mars, with gravity reduced, the heart no longer needs to work as hard. Blood pools differently. The cardiovascular system deconditions, becoming lazy, efficient only for the world it now inhabits. Blood volume decreases. The heart itself shrinks slightly, its walls thinning, its chambers contracting. This is not disease. This is adaptation. The body is optimizing itself for Mars. But in doing so, it is abandoning Earth. When astronauts return from long-duration missions in space, they often cannot stand without fainting. Their hearts can no longer pump blood effectively against Earth's gravity. They experience orthostatic intolerance, a condition where simply standing upright becomes a medical emergency. On Mars, this deconditioning happens more slowly, but it happens nonetheless. And after 18 months, the question becomes unavoidable. Can this heart, this cardiovascular system, ever be retrained to survive Earth again? Then there are the eyes. Intracranial pressure changes in reduced gravity cause fluid to shift toward the head, pressing against the optic nerve, flattening the eyeball, distorting vision. Astronauts aboard the ISS have experienced permanent vision degradation. Some develop a condition known as spaceflight-associated neuroocular syndrome, where the shape of the eye itself changes, leading to hyperopia, an inability to see clearly up close. On Mars, the effect may be less severe, but it is present. 18 months of altered pressure could mean returning to Earth with vision that no longer functions as it once did. Glasses may help, but some changes are structural, irreversible. The eyes, like the bones, like the heart, become relics of a different world. The immune system, too, begins to falter. Isolated from Earth's vast ecosystem of microbes, sealed inside habitats with recycled air and filtered water, the human immune system loses its sharpness. Exposure to new pathogens stops. The body's defenses, trained across a lifetime of infections and exposures, begin to atrophy like unused muscles. Studies of isolated environments, Antarctic stations, submarines, space stations, all show increased susceptibility to infection, slower wound healing, reactivation of dormant viruses like herpes and varicella zoster. On Mars, this effect compounds over months. The immune system becomes complacent, tuned only to the sterile, controlled environment of the habitat. Return to Earth, with its teeming microbial diversity, could trigger immune responses ranging from severe allergies to life-threatening infections. The body, having forgotten how to coexist with Earth's biosphere, may reject its homeworld like a failed transplant. These changes do not happen in isolation. They cascade, intertwine, amplify one another. Weak bones stress the muscles. Weak muscles stress the heart. Poor circulation affects healing. Reduced healing compromises immunity. Each system supports the others, and as each begins to fail, the entire structure becomes fragile. This is not a matter of willpower or determination. This is biology, responding to the environment it inhabits, doing what it has always done, adapting. But adaptation to Mars is abandonment of Earth. The disturbing question, the one that hangs unspoken in mission planning documents, is this: is there a point of no return? A threshold beyond which reconditioning for Earth's gravity becomes not just difficult, but impossible. Some researchers believe that threshold may be somewhere between 18 and 24 months in reduced gravity. Others suggest it could be shorter. The truth is, we do not yet know. No human has spent that long in partial gravity. We have data from microgravity, extrapolations from bedrest studies, simulations and models. But Mars gravity is different. It is enough to slow the decline, but not enough to prevent it. And the critical question remains unanswered. After 18 months on Mars, could a human body survive the return to Earth at all? Imagine the return journey. 6 months in zero gravity aboard the spacecraft, further deconditioned, muscles and bones continuing to waste. Then re-entry. The crushing weight of 1G pressing down after nearly 2 years of lightness. The heart struggling to pump blood upward. The legs buckling under their own mass. The spine compressing under the weight of the skull. Bones, fragile as coral, fracturing under loads they once carried effortlessly. This is not science fiction. This is physiology, projected forward with the data we already possess. Some propose solutions. Artificial gravity aboard the spacecraft, generated by rotation. Pharmaceutical interventions, drugs to slow bone loss, to preserve muscle mass. Aggressive exercise regimens, resistance training for hours each day. But every proposed solution comes with limitations. Rotating spacecraft are enormously complex and expensive. Drugs have side effects, diminishing returns. Exercise can slow the decline, but cannot stop it. And none of these address the deeper truth. The human body, evolved across millions of years to thrive under Earth's gravity, is fundamentally incompatible with Mars. The body in rebellion is not a malfunction. It is the body doing exactly what it was designed to do, optimize for its environment. On Mars, that optimization is survival. But the cost is Earth, the cost is home. And as the months accumulate, as the bones thin and the heart weakens and the muscles fade, the astronaut must confront a possibility more isolating than distance, more final than the journey itself. That return may no longer be a choice. That Mars, intended as a temporary destination, may have become permanent not by decision, but by biology. That the one-way trip was not a matter of fuel or politics or economics, but of flesh and bone, quietly, inevitably, adapting to a world that is not ours. This is the rebellion, not of will, but of biology, not of choice, but of consequence. The human body, after 18 months on Mars, may no longer be human in the way we understand it. It may be something new, something adapted, something that can no longer go home. We have travelled across the solar system in our minds, witnessing the majesty of distant worlds. But now we must return to Mars and confront a question that echoes in the silence of planning rooms and engineering labs across the world. How do you build a spacecraft to leave a planet when no spacecraft has ever launched from another planet's surface? How do you engineer a return journey when every component, every calculation, every backup system must function flawlessly across distances where help is not just unavailable, it is impossibly distant? The Mars Ascent Vehicle. Even the name sounds authoritative, complete, as though such a machine already exists, waiting on some factory floor to be shipped across space. But the reality is far more unsettling. The MAV, as engineers call it, remains largely theoretical, a collection of diagrams, simulations, and hopeful projections. We have never built one. We have never tested one in Martian conditions. We have never launched anything from the surface of another world and returned it to orbit, let alone prepared it to carry human beings on a journey of hundreds of millions of miles. The engineering challenges begin with mass. To escape Mars's gravity, even with its weaker pull compared to Earth, requires substantial thrust and fuel. Current estimates suggest a Mars ascent vehicle would need to weigh between 15 and 30 tons, depending on the crew size and orbital destination. Yet this vehicle must somehow arrive on Mars in the first place. It must survive the descent through a thin, unpredictable atmosphere. It must endure months or years sitting on the Martian surface, exposed to temperatures that plunge to -100 degrees Fahrenheit, dust storms that span continents, and radiation levels that gradually degrade electronics and materials. Here lies the first profound gap in our technology. We do not have engines designed to sit dormant in Martian conditions for 18 months and then ignite with absolute reliability. On Earth, rockets are maintained constantly, inspected, adjusted, kept in climate-controlled environments. On Mars, there will be no ground crew, no technicians, no ability to replace a faulty valve or troubleshoot a sensor reading. The spacecraft must be perfect, not just at launch, but after enduring an environment we barely understand. Then there is the question of fuel. The Mars Ascent Vehicle cannot carry enough propellant from Earth to make the return journey. The mass required would be staggering, multiplying the difficulty of landing on Mars in the first place. This is where the dream of in-situ resource utilization was meant to save us. The plan, elegant in theory, calls for producing methane and oxygen from Mars's carbon dioxide atmosphere using chemical reactors. Yet, as we explored earlier, this technology remains unproven at the scale required. Even if the fuel production works, it must work continuously, reliably, for months, without human intervention, in conditions no factory on Earth has ever simulated. What happens if the fuel production fails? What happens if the reactors clog with Martian dust or a critical pump freezes during the long Martian night? The astronauts would find themselves stranded, standing beside a spacecraft that might as well be a monument, a tombstone of ambition rendered useless by a single mechanical failure. SpaceX has proposed using their Starship vehicle for Mars missions, a spacecraft designed to land, refuel, and launch from the Martian surface. On paper, the concept is revolutionary. A fully reusable vehicle capable of carrying large crews and substantial cargo. Yet Starship's return capability from Mars remains entirely theoretical. As of now, Starship has not completed a full orbital mission around Earth, let alone demonstrated the ability to land on Mars, survive the Martian environment, refuel itself using local resources, and then launch back into space. Each of these steps represents a technological leap, not an incremental improvement. The gap between demonstration and reality is not measured in years, but in entire paradigms of engineering challenges that have not yet been solved. Consider the landing itself. To deliver a return vehicle to Mars with enough fuel, or with the capability to manufacture fuel, requires landing massive payloads with precision. Current Mars landers have delivered rovers weighing roughly 1 ton. A crude Mars ascent vehicle, along with its fuel production equipment and supplies, would weigh tens of tons. The descent systems required for such mass do not exist. The parachutes would need to be enormous, the retro rockets powerful beyond anything currently tested. One miscalculation, one unexpected dust storm during descent, and the return vehicle becomes debris scattered across the Martian plains. But let us assume, for a moment, that the landing succeeds. The fuel production works. The Mars ascent vehicle sits ready, fueled, waiting. Now comes the rendezvous problem. Unlike launching from Earth, where ground control tracks every second of ascent, communicating with split-second precision, launching from Mars means operating with a communication delay of up to 20 minutes. If something goes wrong during ascent, there will be no real-time guidance, no abort commands, no mission control team able to respond before disaster unfolds. The astronauts must rendezvous with an orbiting spacecraft, a habitat designed to carry them back to Earth. This rendezvous must occur in Mars orbit with no margin for error. There are no second chances, no backup launch windows if the first attempt fails. On Earth, if a rendezvous with the International Space Station fails, the spacecraft can return to the ground and try again another day. On Mars, failure means death. The astronauts would remain in orbit, their fuel exhausted, unable to return to the surface, unable to reach the waiting transfer vehicle. They would drift slowly until life support failed. Even if the rendezvous succeeds, the spacecraft that will carry them back to Earth must sustain human life for a journey lasting 500 days or more. This vehicle must provide oxygen, water, food, temperature control, radiation shielding, and waste processing without failure. A single critical malfunction, a clogged water recycler, a failing oxygen generator, and the crew faces a slow, inevitable decline. There are no repair parts available, no resupply missions, no rescue. On the International Space Station, equipment fails regularly. Pumps break, filters clog, computers crash. But on the ISS, replacement parts arrive on cargo missions every few months. Astronauts can perform spacewalks to repair external systems. If a truly catastrophic failure occurs, the crew can evacuate to Earth within hours. On a spacecraft returning from Mars, there is no evacuation. There is no resupply. There is only the equipment you launched with and the hope that nothing critical fails across a journey spanning 100 million miles. Life support systems designed for such duration have never been tested in deep space. The longest crewed missions aboard space stations in low Earth orbit have lasted just over a year. Those missions relied on regular resupply and the psychological comfort of seeing Earth through the window every 90 minutes. A return journey from Mars offers no such comfort. The crew will watch Mars shrink to a point of light, then disappear entirely. Earth will remain invisible for months, growing slowly from a distant star to a blue marble, tantalizingly close, yet still impossibly far. Radiation shielding adds another layer of complexity. The return vehicle must protect the crew from cosmic rays and solar flares for the entire journey. Shielding adds mass. Mass requires more fuel. More fuel requires a larger spacecraft. A larger spacecraft becomes harder to land, harder to launch, harder to build. Every solution creates new problems, cascading through the design like fractures spreading through ice. And then there is the question no one wants to ask aloud. What happens when something breaks 100 million miles from help? Not if, but when. Every spacecraft ever built has experienced failures. Apollo 13's oxygen tank explosion, the Space Shuttle's countless technical issues, the ISS's recurring malfunctions. These were survived because help was near, because Earth's resources were available, because engineers could devise solutions overnight and implement them quickly. On a return journey from Mars, when a critical system fails, the crew has only what they brought with them: their training, their spare parts, their ingenuity. If the solution requires a component they do not have, or expertise they do not possess, there is no rescue. Mission Control can offer advice, but that advice arrives 20 minutes late, long after the crisis may have passed the point of recovery. The spacecraft that can bring humans back from Mars must be more reliable than any machine ever built. It must anticipate failures we have not yet experienced and survive conditions we have not fully imagined. It must function in the freezing vacuum of space, endure micrometeorite impacts, resist the corrosive effects of atomic oxygen in low Mars orbit, and operate every single system flawlessly for more than a year and a half. We have never built such a spacecraft. We do not know if we can. Perhaps the most disturbing realization is this: no space agency has yet demonstrated even a scale model of a complete Mars return system. Not the landing, not the fuel production, not the ascent vehicle, not the rendezvous, not the long-duration life support. Each component exists in isolation, as concepts, as prototypes, as fragments of a vision. But the integrated system, the complete architecture required to bring human beings home from Mars, remains an engineering fantasy, drawn in optimistic presentations but absent from testing facilities and launch pads. The spacecraft that will return humans from Mars probably does not exist yet, and the path to building it is obscured by challenges so fundamental that we are still asking whether return is even practical, or whether we have been planning something else entirely all along. On the journey to Mars, there comes a moment that no simulation on Earth can truly prepare you for. It doesn't arrive with a bang of engines or a flashing warning light. It arrives in silence, somewhere in the black between orbits, when you look back through a small circular window or at a camera feed on a monitor and see your entire world reduced to a single, pale dot. Home is no longer a horizon you can walk toward. It is a coordinate. At first, this is beautiful. Astronauts on the International Space Station describe something called the overview effect, a profound sense of unity and wonder when they see Earth as a fragile blue sphere floating in the dark. But that vision is still intimate. From low Earth orbit, continents are recognizable. Storms curl like white fingerprints Cities glow in familiar constellations of light. You can complete an orbit in 90 minutes and watch the sun rise and set over the same ocean you grew up beside. On the way to Mars, the overview effect begins to invert. Earth shrinks, weather vanishes, continents dissolve into color. One day, you look back, and you cannot point to your country. Another day, you cannot even distinguish land from sea. Eventually, Earth becomes what it once was to our ancestors before telescopes. A star among stars, just slightly brighter if you know where to look. You are not just far away, you are psychologically untethered. Distance in deep space is not only measured in miles, it is measured in minutes and in silence. Between Earth and Mars, depending on their positions in their orbits, radio signals take anywhere from about 3 to 22 minutes to travel one way. That means every message becomes a kind of time capsule. A question asked now is answered by someone who lives up to 44 minutes in your past. On the International Space Station, you can talk with mission control almost as casually as a phone call. A joke lands in real time. A concern is answered before your sentence finishes. Comfort is only a few seconds away. But on the road to Mars, if you say, "I'm scared," the sympathy you hear in response comes half an hour later from someone who can't see your face, can't read your body language, and most importantly, can't reach you. You can stream movies from Earth, but you can't stream empathy. Conversations start to feel like letters shipped over an invisible ocean. Every reply arrives after your emotions have already shifted. There's no such thing as a live argument or a real-time apology. Misunderstandings can stretch for hours. In this delay, a new kind of isolation forms, not the loneliness of being alone, but the loneliness of being unreachable. Psychologists call this communication latency. On paper, it is a technical constraint. In practice, it erodes the idea that anyone else can truly share the moment you are living in. Inside the spacecraft, the universe gets bigger, but your world gets smaller. A handful of humans, sealed in a volume smaller than a typical apartment, moving through the void for months on end, with no exit doors, no fresh air, and no possibility of stepping outside without a spacesuit. And later, on Mars, no possibility of stepping outside without risking death within minutes. Human beings evolved in open systems, forests, plains, coasts, where stress could be discharged with movement. You could walk, run, climb, or simply lie beneath a sky that changed every hour. On a Mars mission, the walls do not move, the ceiling does not rise. The same faces meet you at breakfast, at work, at sleep, every day for years. We have glimpsed pieces of this confinement on Earth. Antarctic research stations endure long polar winters with no sunlight for months. Submarine crews remain submerged for weeks, navigating in darkness, cut off from the surface. These environments are harsh, demanding, and psychologically intense. But their isolation still has an escape clause. In Antarctica, if something goes terribly wrong, rescue is difficult, but not impossible. In a submarine, you are always only a hull thickness away from the air above you. On the way to Mars, that clause evaporates. There is no emergency helicopter, no weather window to wait for, no rapid ascent to the surface. If the mission fractures, socially or mentally, there is no way to bring anyone home early. You are committed to the script, whatever happens inside the capsule. This knowledge subtly infects every interaction. A disagreement is not just a bad day. It is a potential crack that must be carefully managed, repaired, or concealed. because there is no alternate crew waiting in the next room. If someone's mental health begins to decline, help is reduced to delayed words and pre-planned protocols. There are no surprise visits from a therapist, no quiet, unmonitored walk in a park. The stakes of every emotion feel amplified. And beyond the walls, the radiation quietly does its work. Cosmic rays and solar particles do not just threaten cells, they murmur at the brain. Chronic low-level exposure is suspected to impair memory, alter mood, and slowly erode cognitive performance. Combined with poor sleep cycles, artificial lighting, and constant low-level stress, the mind begins to operate under a gentle but relentless pressure. Decision fatigue sets in. On Mars and on the journey there, decisions rarely stop. Every action has risk. How to allocate power, when to perform maintenance, what to prioritize when systems degrade, when to conserve, when to push. Even ordinary routines demand constant awareness, because the environment is perfectly engineered to punish mistakes. Over months, the brain can tire of vigilance. Small oversights creep in. Cognitive testing in long-duration missions has already shown lapses in attention, slower reaction times, and shifts in executive function. The mind itself becomes a resource that must be rationed, like oxygen or fuel. Layered on top of this is a deeper, quieter pressure, the awareness that a return may never happen. No one will board a Mars-bound spacecraft without being told that the plan is to come back. There will be habitat designs, ascent vehicle concepts, in-situ resource utilization schemes, and trajectories mapped home. But the crew will also know, because they are not naive, that every one of those plans is balanced on assumptions, that the return vehicle works, that fuel can be manufactured, that no catastrophic failure occurs on the surface, that funding and support do not vanish on Earth while they are away. The mind does something strange with that knowledge. It begins to live in two futures at once. In one, you return as a pioneer with stories no one has ever lived before. In the other, you remain as a caretaker of the first and only human outpost, because leaving has become technically or politically impossible. This double exposure of fate is its own form of stress. It complicates every long-term thought. Do you plan for life after return or for an existence entirely on Mars? Is this a mission, or is this your final address? The risk is not just fear, it is resignation. In extreme environments on Earth, we have seen what happens when isolation, confinement, and uncertainty converge. Winter overs in Antarctica report spikes in depression, anxiety, and irritability, a phenomenon sometimes called the third quarter effect, when the initial novelty and mid-mission focus give way to a heavy psychological drag. Even with the possibility of evacuation, some individuals experience profound hopelessness. On Mars, the third quarter might come with nowhere to go, and no one who can physically intervene. If a crew member slides towards suicidal ideation, the tools available are limited. Remote counseling, medication, and the fragile support of teammates who are themselves under strain. There is no way to safely restrain someone and rush them to a hospital. No involuntary hold. No emergency psychiatric team waiting at the airlock. The risk is not only that someone may choose to die, it is that everyone else must live with the fact that if they do, there was nothing more that could be done. Designers of Mars missions talk about redundancy in systems, duplicate life support, backup navigation, fail-safe power. But psychological redundancy is harder to engineer. You cannot pack a spare mind in a crate. You can only attempt to build an environment where meaning, connection, and purpose are strong enough to outweigh the abyss that opens when Earth is no longer a world beneath your feet, but a pixel you can cover with a fingertip. There are, however, possibilities that may soften the edge of that abyss. Artificial gravity systems, if they become plausible, could ease some physical stress and help maintain sleep and mood. Virtual reality could bring familiar environments into the habitat, allowing astronauts to walk through simulated forests or family homes. Advanced AI companions might provide immediate conversation even when Earth is half an hour away by radio, a presence that never tires, never grows impatient, and can monitor subtle shifts in behavior in ways humans might miss. Yet each of these tools introduces new questions. Does replacing human presence with artificial companionship help? Or does it underline the absence of real touch and real proximity? Does walking through a digital recreation of your childhood home ease homesickness or intensify it? As Earth fades into a point of light, there is a paradox at the heart of the mission. The journey to Mars is often framed as an act of expansion, of human presence, human capability, human civilization. But for the individuals who make that trip, it is also an act of contraction. Their entire universe collapses into a capsule, a small habitat on a hostile world, a narrow bandwidth of delayed voices from afar. The disturbing physics of a one-way trip to Mars are not only found in equations and fuel tanks, in delta-V budgets and radiation dosages. They are also found in the human mind's attempt to reconcile its ancient need for nearness with other people, with living landscapes, with a sky it recognizes, with the stark reality that, out here, home is just a pixel, and pixels cannot hold you when you break. In that gap between what we can build and what we can bear emotionally, lies a question we have not yet answered. Are we psychologically equipped for true interplanetary exile, even if on paper the rockets work? Before we ask who is willing to go, we may need to ask who is truly willing to never fully come back, even if their bodies someday do. By the time our imaginary spacecraft is parked gently in Mars orbit, its aerobrakes scarred by plasma, and its crew staring down at rust-red canyons and frozen caps of carbon dioxide, an invisible force is already shaping their fate. Not radiation, not gravity, not even the thin, toxic air of Mars. Money. If physics is the universe's first gatekeeper, economics is the second. And on Mars, it may be the one that quietly locks the door behind you. For decades, space agencies and private companies have drawn charts and timelines, glossy animations of spacecraft departing Earth, landing on Mars, and then, with a triumphant plume of flame, lifting off again for home. The arc is always the same: departure, arrival, return. But when we translate those animated trajectories into hardware, fuel, risk, and time, the numbers stop behaving like a heroic story and start behaving like a financial horror. Some internal estimates for a fully crewed round-trip mission to Mars climb beyond 500 billion. Not a flag-planting, picture-taking flyby. A full cycle, launch from Earth, land on Mars, live there, then lift off again and come back. $500 billion. More than the annual GDP of entire nations. More than the cost of building the International Space Station several times over. Enough to fund thousands of Earth-based scientific projects, climate resilience efforts, and medical breakthroughs. Suddenly, the question is no longer, can we go? It becomes, who is willing to pay for you to come back? Designing a Mars mission without a return is like writing a story without the last chapter. It feels wrong, it feels incomplete. Yet, from the cold vantage point of the balance sheet, the moment you add a return ticket, the mission transforms. It is no longer just a daring expedition. It becomes a logistics nightmare. A one-way mission needs a spacecraft that can reach Mars and keep humans alive on the surface. Habitats, life support, power, food, tools. Difficult, but conceptually simple. Add a return, and everything multiplies. You no longer need just a lander. You need a lander that brings down not only people and supplies, but also, somehow, either their ride back home or an entire factory to build it. You need fuel tanks on Mars, or the means to harvest resources from the Martian air and ice. You need ascent engines tested in an environment no one has ever flown from before. You need redundancy for all of it, because if any link breaks, there is no repair shop, no backup launch, no quick replacement. Every kilogram of return hardware you land on Mars had to fight Earth's gravity first. Rockets on rockets, tanks inside tanks, margin stacked on margin. The rocket equation, already cruel, becomes unforgiving. Designs that looked ambitious now look absurd. Mission planners quietly admit it. The ability to leave Mars again does not merely double the challenge. It can triple or even quadruple the complexity, the mass, and the cost. And yet, if you remove that one piece, if you accept that the mission is one way, everything changes. Not morally, not emotionally, but economically. In that world, we stop thinking in terms of round-trip exploration and start thinking in terms of initial settlement. The mission is no longer about coming home. It is about building a new one. From a purely financial perspective, colonization has a strange, ruthless logic. A one-way mission does not have to deliver fuel for departure. It does not need an ascent vehicle robust enough to launch from Martian gravity back into orbit. It can trade the heavy machinery of return for more habitats, more tools, more food, more redundancy for survival. The question shifts from how do we get back to how long can we last? To some planners, that trade feels efficient. A $200 billion mission that seeds a permanent settlement might be judged a better investment than a $500 billion mission that sends a handful of people to Mars for a few years and then brings them home, leaving nothing behind but tire tracks and a few discarded modules. In boardrooms and budget hearings, a disturbing calculus begins to emerge. If you are going to risk lives and reputations on such a venture, why not design the mission to last? Why not aim for permanence, even if that permanence is born from the impossibility of returning? But who exactly is supposed to pay for any of this? For over half a century, deep space has been the domain of governments. Apollo, the space shuttles, robotic probes to the planets, all funded not by profit-seeking companies, but by nations willing to spend public money on prestige, science, and strategic advantage. Today, the story is different, but not completely new. Private companies build rockets and spacecraft. Billionaires talk openly about Mars as humanity's backup drive. Animated videos show sleek ships refueling in orbit, hopping from planet to planet like airports in the sky. Yet, even in this new era, the deeper one looks, the more the old reality returns. The expensive parts of exploration, long-duration life support, radiation shielding, planetary habitats, are still heavily subsidized or directly funded by governments. Commercial space thrives in Earth orbit because there is a clear economic return. Satellites, data, communications, tourism. Mars has no such market, no paying customers, no cargo demand, no existing economy to plug into. From an investor's perspective, a Mars return mission is all cost, no revenue. A government might fund a Mars mission for national prestige, scientific achievement, or the hope of driving technology forward. But would it authorize spending $500 billion not once, but multiple times for round-trip crews to Mars, while hospitals, schools, and infrastructure on Earth compete for the same funds? The uncomfortable answer is probably not, at least not often. And so the idea of a one-way mission slips back into the conversation, no longer as science fiction, but as budget optimization. We have seen glimpses of this before. In the early 2010s, a project called Mars One captured global attention with a bold promise. Volunteers would be sent to Mars on a one-way trip to start the first human colony. No return, no rescue, just a permanent foothold on another world, broadcast as a reality show. Thousands applied. The ethical questions erupted just as fast. Is it acceptable to send people to Mars knowing they will never come back? Does informed consent make it moral? Or does the inability to rescue them turn the entire mission into a televised slow-motion disaster? Scientists question the feasibility. Engineers question the timelines. Ethicists question the premise. Eventually, Mars One faded, leaving behind a cautionary tale. The world may be fascinated by the idea of one-way pioneers, but accepting their fate as final remains deeply unsettling. And yet, in the background, mission concepts continued to evolve. Some proposals from serious, credible groups quietly include options that resemble one-way frameworks. Crews stay for very long durations, perhaps rotating back only if later technology permits. Habitats are designed to be permanent, not temporary. No agency issues a press release saying, "We might not bring you home." Instead, the language becomes softer, indefinite duration, long-term surface operations, pathways to sustainability. Behind those phrases lies a stark physical truth. Rescue on Mars is not just hard. It is, for early missions, essentially impossible. On Earth, if an expedition is stranded in Antarctica, another plane can be dispatched, or a ship can brave the ice. On Mars, a rescue launch would itself be a multi-year campaign. You would need to assemble a new rocket, launch it from Earth, wait for planetary alignment, journey for months, land precisely where the original crew is located, and then somehow have enough fuel and hardware to bring everyone home. Every step in that chain is vulnerable to delay, failure, or miscalculation. The cost of such a rescue would rival the original mission. No politician will easily sign off on a second $500 billion emergency flight to save a handful of people when that same money could avoid suffering for millions on Earth. The physics of orbital mechanics and the realities of national budgets converge on one conclusion. If something goes wrong on Mars, the help you imagine from movies, the cavalry of rockets streaking through the sky, will not be coming. The first crews to go will know this, whether it is said aloud or not. They will live with the understanding that if they stay, it is probably permanent. If they leave, it will be because a returning architecture, developed years later, finally exists and is funded. Underneath all the technical debates, a single question lurks in every funding meeting. Is return worth the cost for the first missions? If the goal is pure science, robotic missions are cheaper, safer, and astonishingly capable. If the goal is national prestige, a single one-way or long-stay mission that plants a permanent flag might be more politically powerful than a cautious visit and leave mission. If the goal is the survival of our species, building a second self-sustaining home may take precedence over ensuring every pioneer gets a ticket back. None of this means we will never have round-trip flights between Earth and Mars, just as we eventually built routine flights across oceans once considered deadly. But history suggests that the earliest crossers of any great frontier pay the highest price and rarely see the full benefits of the worlds they open. Those who first crossed unknown seas did not sail with guaranteed rescue convoys behind them. Many simply vanished. Their voyages continued only in the maps and knowledge they left behind. The difference now is that we can see these risks in advance. We can simulate them. We can plan for them. And still, we may choose to send people anyway. The economics of impossibility does not slam the door on Mars. It simply clarifies the terms of the bargain. For early explorers, the question will not just be, can you survive the journey, but is the chance to walk on another world worth knowing that the universe and our budgets may never pay for your return? As we move closer to that decision, the disturbing truth emerges quietly. The one-way ticket to Mars is not just a dramatic idea. It may be the only financially and physically realistic path we have, at least in the beginning. The plan was always sold as a round trip. Go to Mars, plant a flag, do some science, and come home to applause and documentaries. But when you start reading the fine print of our most serious mission concepts, a different picture begins to emerge. A quieter, unspoken assumption takes shape between the lines of technical reports and glossy animations. We are not really planning to bring the first humans back. Not because we are cruel or careless or blind to the risks, but because the physics, the engineering, the biology, and the economics have cornered us into a harsh compromise. To step onto Mars in the near future may mean never stepping on Earth again. And the unsettling part is not that this is true, it's that we rarely say it out loud. Look closely at current mission architectures. NASA studies with acronyms like DRA, DRM, and long-range exploration architectures. Space agency roadmaps from Europe, China, and private concepts from companies you've heard of, and some you have not. Almost all of them share a quiet symmetry. The outbound journey is detailed. The surface stay is described. The science is rich. The return is vague. Sometimes it's a dotted line on a trajectory chart. Sometimes a paragraph. Crew departs Mars using ascent vehicle pre-fueled by in-situ propellant production. The diagrams are clean. The reality is not. Those ascent vehicles, the fuel factories, the storage systems, the redundancy needed to bet human lives on a launch from another world. Most of that hardware has never been built, let alone tested in Martian conditions for years at a time. So the architecture papers make a choice. They assume success. The ascent vehicle works. The fuel is there. The return window is met. It is all mathematically consistent, physically plausible, and entirely hypothetical. In the space between plausible and proven lies a quiet truth. If anything in that chain fails, it stops being a round trip and becomes a one-way mission by default. Nowhere is this tension clearer than in SpaceX's vision for Mars. The company does not describe a heroic there-and-back expedition. It speaks of a city, 1 million people, greenhouses, factories, foundries, fleets of starships parked on the rust-red plains like an alien harbour. Listen closely to how that story is told. The design of Starship is not optimized around returning a small, fragile crew to Earth. It is optimized around sending large masses to Mars and building up infrastructure over many years. Cargo first, then uncrewed systems, then humans who are expected to live there, work there, and in many cases, die there. The return capability is described as an option, not the core mission. Starships can, in principle, refuel on Mars using methane and oxygen produced from local resources. They can lift off again and glide home through Earth's atmosphere. But the entire economic logic of the Mars colony concept leans the other way. Stay, expand, grow. A frontier, not a round-trip tour. It is not framed as a suicide mission. It is framed as emigration. Generations before us boarded wooden ships and crossed oceans, knowing they would never see their homeland again. Not because they were forced to, but because their destination was not a place you visited. It was a place you became a part of. SpaceX's language reflects that older pattern. The first flights are portrayed not as expeditions with guaranteed tickets home, but as the opening of a migration. You go to Mars to live on Mars. Maybe later there will be traffic both ways. But if you are among the first, you are more settler than guest. NASA, by contrast, chooses its words with deliberate care. Publicly, official Mars mission profiles are conjunction-class missions with well-defined outbound and inbound legs. The architecture is framed as go, explore, return. NASA has a duty, by law and culture, to bring its astronauts home. So the language becomes very precise. You will hear phrases like sustained presence and long-duration surface operations. Talk of pre-positioned assets and incremental build-up of infrastructure. You will see timelines that extend beyond the first mission toward a campaign of Mars expeditions. It is the vocabulary of a foothold, not a flag planting. But NASA also knows that their first crews will be living on a knife edge of reliability. In presentations, you'll see multiple ascent vehicles pre-deployed, backup fuel production units, redundancy upon redundancy. Not because they expect to rescue crews with a spare rocket like a movie, but because the cost of failure is absolute. Behind the careful optimism lies a fact few press conferences dwell on. If anything critical fails and cannot be fixed with what you brought, there will be no rescue mission racing across 140 million miles in time. A Mars mission is not like the ISS, where another spacecraft can arrive in days. It is a tightly choreographed alignment with orbital mechanics. If you miss your ride home, the next chance may be years away. Ethically, this forces a question we are not used to asking in spaceflight. Should people be allowed to go knowing that the plan, or the probability, leans toward never returning? Some argue that forbidding one-way missions would be paternalistic. Adults already choose careers that shorten their lives: deep-sea divers, test pilots, mountaineers, soldiers. If a person fully understands the risks and still volunteers to step onto Mars with no guarantee of coming back, who are we to deny them that choice? Others counter that informed consent in this context is nearly impossible. No simulation can reproduce the isolation of watching Earth shrink to a star and knowing it may never be anything more than that again. No training can fully prepare you for the knowledge that if a valve sticks or a habitat wall cracks, the nearest emergency room is an entire planet away. There is also the issue of precedent. If governments or companies normalize one-way trips, do we risk turning human lives into expendable components of an exploration agenda? Or are we finally being honest about what exploration has always really cost? Looking back, we find that history is more comfortable with one-way journeys than we are. Polynesian navigators set out into the Pacific in canoes with no satellite images, no GPS, and no certainty of land. Many undoubtedly never returned. Medieval pilgrims walked to distant shrines until their strength or their money ran out, often dying far from home. Early Antarctic explorers wrote their letters knowing they might be read as epitaphs. For them, the unknown was not a hazard to be eliminated. It was the price of discovery. Mars may be our first explicit return to that older bargain on a planetary scale. The astronauts we see in concept art, stepping down ramps into orange dust, will likely carry within them a private understanding. The odds favour staying. Even if their mission patch shows an arc out and back, the universe does not sign contracts. The physics of launch windows, the harshness of radiation, the fragility of life support systems, the slow degradation of bodies in reduced gravity, all of these tilt the table toward permanence. The first Martian cemetery, whether marked or not, will not be an anomaly. It will be a milestone. This does not mean we are doomed forever to one-way trips. Technology is a moving target. Nuclear thermal propulsion could cut travel times, reducing radiation doses, and making emergency trajectories slightly less impossible. Autonomous construction systems might build reliable fuel depots and ascent vehicles years before humans arrive. Closed-loop life support could lessen the mass penalty of round-trip missions. Over decades, a mature Mars infrastructure could transform the equation. A network of habitats, greenhouses, machine shops, and fuel plants could make Mars less a dead end and more a transfer station. Crews might rotate, not settle. Children born on Mars might visit Earth the way earlier generations took steamships across the Atlantic. Rarely, but not impossibly. Yet that future, if it comes, will be built on the backs of the first to go. The people who step out of the first spacecraft may never see that more forgiving era. Their lives will be spent turning Mars from a destination into a place that has a normal, a routine, a history. In that sense, the disturbing truth is not only that we are quietly planning one-way trips, it is that becoming an interplanetary species may require us to recover something we have almost forgotten: the willingness to accept that some doors, once opened, do not close behind you. That some journeys are not round trips, but transformations. That sometimes exploration is not measured in how far you travel, but in how completely you let go of the world you started from. When the first humans leave Earth, orbit bound for Mars, the official documents will speak of mission phases and return trajectories. But somewhere, deep inside the spacecraft, someone may look back at the shrinking blue circle and understand what the paperwork cannot say. For them, this may not be a visit. It may be the last time they ever see home. By now, the shape of the problem is clear. It isn't a single wall that stops us from coming back from Mars. It is a maze of walls, layered on top of each other. The rocket equation turns every extra kilogram of return fuel into an exponential penalty. Orbital mechanics stretches a simple round trip into a multi-year dance with moving planets that rarely align in our favor. Radiation gnaws at DNA day after day. Muscles and bones quietly dissolve in low gravity. We dream of making fuel from Martian air and ice, while the engineering blueprints for a true Mars ascent and return vehicle mostly live as simulations and artist impressions. Each obstacle alone is daunting. Together, they begin to look like a verdict. Returning from Mars is not impossible in principle, but it is very close to impossible with the tools we actually have. And yet, someone will volunteer to go. Somewhere, a future astronaut will read the risk assessments, watch the simulations of failed ascent stages, understand that contingency habitat is a polite phrase for "you might never leave," and still sign their name. Not out of ignorance, but out of a strange mixture of courage, stubbornness, and the human instinct to stand where no one has stood before. We often ask, is that bravery or madness? But history suggests the answer is usually both. The first people to cross oceans in fragile wooden ships, the climbers who step into the death zone on Everest, the polar explorers who hauled sleds into white nothingness. They all gambled that the story was worth more than the safety they were leaving behind. Mars will be the same, only stretched across millions of miles and multiple years, with Earth shrinking from a familiar world into a pale star that cannot help you in real time. If we accept that, then the question shifts, not can we guarantee a return, but what price are we, as a species, willing to pay for a foothold beyond Earth? Because Mars is not the end of the road. It is the first rung on a very long ladder. A civilization that learns to survive a one-way trip to Mars learns how to live off-world, to mine ice, build closed-loop life support, grow food in dust that never knew rain, and protect fragile biology inside a hostile sky. Those skills echo outward, to asteroids, to moons, one day even to the cold light of interstellar space. There is room for hope here. New propulsion concepts, nuclear thermal rockets, high-efficiency electric drives, even speculative fusion or beamed sails, could compress travel times and reduce how much mass we must throw uphill. Advances in radiation shielding, biomedical engineering, and artificial gravity might turn a suicidal journey into a survivable one. In-situ resource utilization on Mars could evolve from experimental rigs into something as ordinary as a power plant on Earth. When those pieces finally exist together, a true round trip to Mars might feel less like a stunt and more like a difficult but repeatable expedition. Until then, the frontier will ask for sacrifices, not as a punishment, but as a law written quietly into the physics of space and time. Every new horizon humanity has ever crossed has been paid for, in lives, in years, in irreversible choices. Mars will be no exception. If you've stayed with this journey all the way to the end, I'd like to hear from you. Tell me in the comments, where in the world are you watching from, and, knowing everything you know now, would you still take a one-way ticket to Mars? If you found this video thought-provoking, consider giving it a like and subscribe so you don't miss future deep dives into the strange edges of physics and space exploration. And if you'd like to support the channel a bit more directly, there's an optional YouTube membership you can join, completely voluntary, but it helps make more videos like this possible. In the end, becoming an interplanetary species is not just an engineering project. It is an ethical decision, a bet on the kind of future we want. Somewhere between courage and folly, between hope and hard vacuum, lies the real cost of Mars. And sooner or later, someone will pay it.